Hello out there, all you fine people on the internet. I am I Can Science That, and today I want to investigate what is science. Is there a scientific method? What is it? And how do we know if we're doing it? So let's science some science. I'm going to Google it. I want to know the scientific method. Now, here we go. People are going to tell you out there that they know what the scientific method is, and you are doing it wrong. So let's investigate that very topic right here. I'm going to be completely open. I'm going to be completely honest. You could do this yourself, but I know you're not going to. So I'm going to do it on a video for you. You can do it with me. Follow along. Just to make sure I am not cherry picking my definitions, I'm going to use Google, and I'm going to go through from top to bottom and look at every one of them. We'll look at several. You know for sure that I'm not digging down to the one I want to find, because I'm going to start at the top. Here we go. The scientific method. First one is a featured snippet, not an ad, so I think that counts. This is what Google wants me to do. You know what? Somebody out there in internet land, explain to me, what is a featured snippet? You know what? Let's just find out right now. What is a featured snippet? It does not look like these are paid. It looks like this is what Google thinks is good. It looks like to me. That was a very cursory look. So if I'm wrong about that, let me know. I don't want to be following the ads. I want to follow the actual hits here. Scientific method, definition, and steps. Britannica. Okay, this is where it took me to. Here it is, a picture. It took me a second to get it. There it is. Go away, cookies. Oh, go away, ad. Here we are. So here are the steps. It's a diagram. We start with collect information, make observations, ask questions. We formulate a hypothesis, design experiment to test hypothesis, conduct an experiment, draw some conclusions. What are we going over here? Observing some results, and we're comparing some things. We're drawing some conclusions. Wow, that's kind of a mess. Okay, let's see what the next one is. ScienceBuddies.org. What have you got for me, Science Buddies? Science Buddies has a similar flowchart. This one's a little bit more top to bottom. What do they got? Ask a question, do background research, construct a hypothesis, test with an experiment, procedure working. Oh, okay. What if the procedure's not working? Something in there. Analyze and draw conclusions. And then they got this loop back up. Do it again. Okay. Who's next? Wikipedia. Can't go wrong with Wikipedia, right? This is quite the article. And actually, you know what? If you just read this Wikipedia article, you'll get a lot of background. But let's just see if we can find what the steps are. Process. Here we are. The process. Oh my gosh. Where's my diagram? No diagram. Okay. The overall process involves making conjectures, hypotheses. Okay. Deriving predictions as well as logical consequences, and then carrying out experiments based on those predictions. Okay. There are difficulties in a formulaic statement of method, however. So we'll come back to it, but for some reason, Wiki doesn't want to give me a series of steps. The others gave me flowcharts and diagrams with steps. This one doesn't want to give me any steps at all. So, all right, what's next? Khan Academy. I've heard of them. Khan Academy. There we go. Here's a series of steps. This is what we were looking for. We got 6 steps. We start with an observation, then we ask a question, form hypothesis, make a prediction, test the prediction, iterate. Okay, why doesn't this one have experiment? There's no experiment here. Why is it different? Let's keep going. Let's see at least one more, maybe a couple more. Stanford, that's legit, right? That's like college level stuff. Oh my gosh. Let's see. statistical methods, methods in practice, discourse on the scientific method. This looks like it's gonna be some reading. And there's another reading here on science and pseudoscience that we should probably read. If you are serious about this, now I'm just blasting through this, right? To make a point that I'm gonna get to. But if you really wanted to know what scientists actually do, what do they really consider their methods, this is a good place to start. This is from Stanford. This is a college. It's an American university and very highly respected. Read this, though. What you're not going to find here is cartoons and diagrams made for children. These other things, they look like they were made for children. This one from Science. This is Science Buddies. It's something called sciencebuddies.org, and it's at the top of the list from Google. Why do these things look like they are made for children? The reason these things look like they were made for children is because they are. In reality, real scientists don't follow a flowchart. They don't have a series of checklists that they follow. They don't have a method that they follow to do science. That's not how real science happens. These diagrams are written for school children. They're drawn for school children. Hypothesis is a big word, and you learn it at this point, and then you try to leverage that learning. What we really do is described in here, and that says how these are carried out in detail can vary greatly. Let's look over here. I like this one. The scientific method in science education and as seen by scientists. This is suggested reading for everyone who wants to engage in the debate of, is this the scientific method or is it not? Occasionally, scientists make sweeping statements about a simple and distinct scientific method, as exemplified by Feynman's simplified version of conjectures and refutations method presented, for example, in the last of his 1964 Cornell Messengers lectures. Now, if you haven't caught that video, it is a hoot. Go watch it. I love that video. I love Feynman in general. Really great stuff. Go watch it. However, just as often, scientists have come to the same conclusion as recent philosophy of science, that there is not any unique, easily described scientific method. Let's say that again. There is not any unique, easily described scientific method. And if you go on to dig deeper and actually read about what science really is, you'll find out that there's lots of different ways that we do science. Science is a lot of things. Science starts with the body of knowledge that we teach in science classes. Yeah, that's part of science. But also science is experiments. Science is hypotheses and testing. Science is observations. Science is measurements. We take measurements. We do regressions. Science involves a lot of mathematics. What we do not have is a ritual that we perform in order to conduct science. Science doesn't work that way. Science is the process of trying to decide what is correct from what is not correct, trying to separate your expectations from reality. Because we all know that intuition is not perfect. Sometimes we expect things should work in a certain way, and Mother Nature just does not want to agree with us. And we're all very surprised. We raise our eyebrows, and that's when the scientists get excited and say, I have made a discovery. And so then the whole scientific method is designed to try to explain to school kids how we do that. let's take a closer look at a few of those and see if maybe I'm not right about that. Back to the beginning. We'll do them in order. The very first hit was Britannica. Okay. And we had, took me a second to get it. There it is. We have the flowchart version. The flowchart. Just, let's make this real simple. What are the key steps here? Observations, questions, hypothesis, design experiment, conduct experiment, compare results, draw conclusions, report findings. Okay, they're talking about peer review there. Okay, so we had like 8 steps there, at least 8 steps, and that's what the major hits were. Okay, what was next? Science buddies. Science buddies, go away thingy. Science buddies. All right, what have they got? Ask a question, do background research. That wasn't on the previous one. How come that's not on there? You know what's not on here? The other one started with observation. This one doesn't have start with observation. It says ask a question. So these aren't the same. This is different. They both have, that one said design a hypothesis. This one said, no, what did it say? It said formulate hypothesis. This one says construct hypothesis. I think we can call that the same. Test with an experiment. It doesn't say design an experiment, but this one said design experiment, conduct experiment. This one says test with an experiment. Can we say that's the same thing? Maybe. Okay. This one talks about the procedure, whether the procedure's working. The other one doesn't mention that. All right. They both talk about drawing conclusions. And then what do we do with the conclusions on this one? We say communicate results. Hey, that's pretty good. So this one also shows a loop back. Like if the results don't match the hypothesis, what do they tell you to do? They say to communicate your results, but they also say going back to tweak your hypothesis and do another loop. Does this one have a loop in here? Compare, draw conclusions. Yeah, maybe. It looks like oh, here it is. Refine hypothesis is over here. So that's where that is. Okay, so there were some steps that they shared in common, but also some differences. Let's look at the third one. Oh, Wikipedia. Well, I'll have to hold that because they didn't have a diagram. They wouldn't give us steps. We'll get to that. Khan Academy. Khan Academy has make an observation. Here's the observation is back. They have ask a question. That's good. All 3 have that ask a question. Form hypothesis. All 3 had form a hypothesis. But this one, it's got something neither of the others did. It says make a prediction. Was that in here? Was there a make a prediction? No, that doesn't mention make a prediction. How about this one? No, it doesn't say that. How can this one doesn't talk about communicating the results either. These are not the same. They're all different. Every single time you go and look for what the scientific method is, it's different. Now, think about that for just a minute. Why is that? Why is that? Could it be that there is no one single specific scientific method that we all follow? Maybe science is not ritualistic. It doesn't follow a recipe. What makes science special is that we are going to answer a question objectively. We're going to find out for real whether this is true or not. And we'll start with a question. We can't answer that question unless we start with a question. And so some of them talk about making an observation. Others don't mention the observation. I've had people come to me and say, your science is not science because you did not start with an observation. Where is that coming from? I mean, why do I need to start with an observation? Some of them do make that inclusion. They say make an observation. Some don't. Why is it even there? It's there to tell the student that that's how it traditionally starts. It starts with somebody sees something and says, hey, what's going on with that? That thing that I just saw makes me ask a question, makes me wonder. I look up at the sky and I ask the question, why is the sky blue, right? That's that. Now, do I really need to formalize that? When I submit a paper to the Journal of Nature, do I list what my observation is in step one? Step one, my observation. No, we don't. We don't. It's just there for explanation purposes to tell the story of how that works. We probably do have a question, though, that we'll want to outline. We'll want to put that in the abstract. What is it that we're trying to find here? Like, is the sky blue? Or why is the sky blue? Something like that. And then they all share this concept of the hypothesis. And some of them mention it must be testable, right? We're going to do a test to see if the hypothesis is true or not. And then some of them mention this prediction, but others do not mention the prediction. Why don't they mention the prediction? Why do we need a prediction? Do we need a prediction? The truth is, sometimes we don't. Sometimes we do, sometimes we don't. Based on the hypothesis, in this example of what science might be, we are teaching the concept of logic. This is a basic logical flow that just goes, if A, then B. If not B, therefore not A. Okay? And that is the basic logic that all of these things are designed to outline, but that is maybe a little bit too abstract for a grade school science education or even a middle school science education. And so we give these sorts of recipe-looking answers. Let's go now to the Wikipedia and see what they have to say, because they refuse to give us steps. So let's see here. Blah, 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 blah. There are difficulties in a formulaic statement of method, however. Though the scientific method is often presented as a fixed sequence of steps, these actions are better considered as general principles. Note, citations, they're right here. Go follow them for yourself. Not all steps take place in every scientific inquiry, nor to the same degree. Right? So some types of scientific inquiry use certain steps, and others don't use those steps. And they are not always done in the same order. And then they do have sort of, the steps here, sort of. There's that question that we generally do start with. Here's the definition of what a hypothesis is, or, a description of what a hypothesis is. This is how the prediction comes in and how the testing is done. Prediction, what is that all about? This step involves determining the logical consequences of the hypothesis. One or more predictions are then selected for further testing. The more unlikely that a prediction would be correct simply by coincidence, then the more convincing it would be if the prediction were fulfilled. What does that say? Let's look at that again. First of all, what this says right here, I was just talking to somebody on YouTube about the idea of do I create the hypothesis first or do I create the experiment first? Right? They wanted to say, give me the experiment and then I'll tell you what my hypothesis is. We can reorder things. We absolutely can, because scientific method is not a ritual. It is not a rigorous set of dogma that we have to follow. It's not a checklist or a recipe. We can mix things up any way that suits our fancy. But when we teach this, the reason that we teach hypothesis first and then experiment is because we are designing an experiment specifically to highlight this prediction here. The more unlikely that a prediction would be correct simply by coincidence, then the more convincing it would be if the prediction were fulfilled. What does that mean? I don't know. Let me go to my old jam example from my Kritical Kwickies series. If you haven't seen my Kritical Kwickies series, they're very quick and I think they're a lot of fun. You go check them out and tell me what you think. I have one in there where I have jam. I have some jam and I don't know what kind of jam it is. So I make a hypothesis. I hypothesize that it is strawberry jam. Now, based on the fact that it is strawberry jam, I predict that it would be red. If it is strawberry jam, it will be red. That is my prediction. However, it's a very poor prediction because coincidence. It could also be raspberry jam. Raspberry jam would also be red. So if I went and I did a spectrographic analysis of the color of my jam and I said, oh yes, it's definitely red, I have accomplished very little. I have merely confirmed indeed it is red. So what? Does that mean that it is strawberry? No, it doesn't, right? That means that it's red. It could be red because it's strawberry. It could be red because it's raspberry. We would want to highlight some feature of strawberry jam that is unique or at least unusual or unexpected, right? If it was something else. And so, obviously taste the damn stuff, right? If it tastes like strawberries and it's red and it has seeds, then we're going to believe that it's probably strawberry, right? And it's going to take significant evidence to the contrary to convince anyone that you made a raspberry jam that tastes distinctly like strawberries, right? Okay, so that's why we do the hypothesis first. We make the predictions, and based on the predictions, we design an experiment, right? That's why we do it in that order. Okay, here we go, right here. Ideally, the prediction must also distinguish the hypothesis from likely alternatives. This is what I'm talking about with the raspberry versus the strawberry jam. Or if you're following along, this is precisely my point with the Eggsperiment from our friend. If you're following me, you know who did the Eggsperiment. I'm not going to name names, but you know whose Eggsperiment I'm talking about. The problem with the Eggsperiment is the prediction that adding salt to water causes the egg to rise does not distinguish the hypothesis from the likely alternative. The hypothesis in this case is that there's something called relative density disequilibrium, and that caused the egg to rise. The likely alternative is that the science they taught us in the textbooks, the stuff about gravity and buoyancy and so forth, whether you believe that or not, it must be considered a likely alternative. After all, that is what is in all the textbooks. That makes it an obvious likely alternative that we should consider. And guess what? It makes the exact same prediction. Therefore, this particular prediction is not useful to us. If two hypotheses make the same prediction, observing the prediction to be correct is not evidence for either one over the other. So there you go. That's why the Eggsperiment, it has no value. It is perfectly, well, that's not fair. The Eggsperiment is a perfectly good experiment. It's a great tool and it's pretty cool. You can do that in the science classroom. You can do that at home in your kitchen and really, amaze the kids with how this works. But you didn't prove something called relative density disequilibrium with that one. Normally, people would say that they had just proved buoyancy. The rules of buoyancy that are taught in classrooms and where they do that very same experiment to teach buoyancy. Here, this one's good. What do we do based on these results? Do we say, if the prediction does not match, we strike that hypothesis? That's wrong. That's what Feynman says, right? If it doesn't match, it's wrong. Let's see what Wikipedia has to say. If they agree, confidence in the hypothesis increases. Otherwise, it decreases. Sounds a little bit more nuanced than what Feynman had to say. You know what? I love Feynman, and I love that quote from Feynman, and I'm going to stick with it because it's fun, it's simple, it's understandable. But the truth is here. The truth is what Wiki has to say. If your prediction does not come true in your experiment, does it mean your hypothesis was wrong? It means it's not looking good, right? But maybe you missed something. That's why we do the peer review. That's why we check. Maybe somebody else can come along and say, your test, you designed your test incorrectly. There's a flaw in it. Your test does not show what you think it shows. And that happens all the time. There was the very famous example of the neutrinos from CERN that were initially measured to be moving faster than the speed of light. And so what did they do? Did they announce to the world, we've discovered faster than light travel? Did they announce, we have overturned special relativity? No, that's not what they did. The press may have tried to make it sound like that, but what the scientists did was they published their preliminary results, and they asked people in the community, the scientists, to go over it and find what they explicitly stated was certainly a mistake. And indeed, the mistakes were found. The mistakes were found and corrected, and lo and behold, everything suddenly matched predictions. That's how mature people behave. And so we should acknowledge that as well. Okay, agreement does not assure the hypothesis is true. Under no circumstances does confirming your hypothesis prove that your hypothesis is true. And the reason for that is future experiments may reveal problems. Okay, and then we're going to talk about Karl Popper. Karl Popper, big deal. Definitely, if you're interested in this topic, look into him. He's very influential. He said basically the real strength is when you can falsify a hypothesis. So you can never say for sure this is definitely true because someone's going to come along down the line and say, not in this one case. I have a tweak for you. Your original hypothesis wasn't perfect. But you know what Karl Popper said, and I happen to agree with, is if you can show that the hypothesis was definitely wrong, that will stand. That will stand into the future, and we can say, okay, that was not correct. If we can eliminate all the not correct things, then what we're left with is the most likely things, right? That is my rant on the scientific method. So what's this all about? The reason for this is there are certain people on the interwebs who are very, very uptight that we must follow their version of the scientific method. That if we're not following their version, mind you, of the scientific method, then we are not doing science. So I hope that if you've watched this at all, the thing you come away with is the realization that that is not correct. That is not how we decide how you are doing science or whether you are doing science. It doesn't work that way. And I would hope, I don't do debunks and I don't do trash talk, but you know who I'm talking about or which group of people I'm talking about, and I would hope that you will not trust them because they know this too. This is Wikipedia. This is not a secret. This is Stanford University on their public web pages. This is not a secret. And you know as well as I do that those same people who have shouted at you that you are not doing science because you're not doing it their way, they've read this too. And now I hope you understand that those people are not being honest with you. They are trying to shut you down. They're trying to close you down and box you in so that they can control your framework. I am not going to say that you are not doing science correctly and therefore your ideas do not have merit. If somebody tries to tell you that what you're doing does not conform to the scientific method, or it doesn't fit certain strict definitions of words that they have chosen for you, then they are not being honest with you. Maybe they're not even being honest with themselves. It's always hard to tell, but you can be certain that somebody who shuts you down for those kinds of ritualistic, dogmatic reasons is not being honest and does not deserve your trust. Next time, I'll do a rant about definitions. I'm thinking about that one because, boy, does that happen a lot. See you next time.